In our final video in our series on double displacement reactions, we're going to consider a phenomenon called compound reactions, in which a double displacement reaction occurs and pretty much immediately after has a follow-up second reaction involving one of the products produced in the original double displacement. And we can actually use an example of a very common reaction that's done in elementary school, because you can do this reaction from home as long as you have baking soda and vinegar to drop into it. Now, we need to know what the chemical formulas of these chemicals are to predict what the reaction is. So as it turns out, sodium hydrogen carbonate, or sodium monohydrogen carbonate, is the chemical formula for baking soda, and this acid here, which is actually an organic acid, which is what we call acetic acid, is the chemical formula or the active acid in vinegar. And we can see that sodium monohydrogen carbonate is clearly going to form our AB compound, but this acid is a little bit hard to see because the hydrogen that it loses is actually at the end, so this is actually our CD compound here. And when we get a double displacement reaction that occurs, we would end up having our cation in one replace what is going to be the cation in the other. So here, because hydrogen ionizes in order to form an H plus ion, sodium would replace hydrogen in acetic acid, and then the hydrogen would replace the sodium in sodium monohydrogen carbonate, and the salt that we would get here, at least the compound that looks like a salt, would look like this, where we have acetic acid as a polyatomic ion. This polyatomic ion is what we call acetate, and we have sodium acetate that forms like this, where sodium is of course the cation and acetate is the anion, and because each of them have a charge of +1 and -1, we don't actually need to modify the chemical formula other than this. Now, if we add this hydrogen onto monohydrogen carbonate, we would get another acid that forms here. So H2CO3 is the chemical formula for carbonic acid, and we can see, because the two anions or the two cations, whichever you prefer, switch places, this is technically a double displacement reaction. Now, when you do the baking soda and vinegar experiment, one of the most obvious signs that a chemical change has occurred is a very, very large amount of bubbles that form, particularly if you add soap to trap the gas inside. So bubbles imply that we have made some kind of gas in this reaction, but carbonic acid is an acid, meaning that it's going to dissolve in water, and sodium acetate is a salt, and because sodium is an alkali metal, we can use the solubility table to show that this compound would also dissolve in water. So where is the gas that was produced? Well, most elementary school students can tell you that the gas bubbles are a result of carbon dioxide that is being produced. So where does this carbon dioxide come from? Well, the answer is the carbonic acid here that is produced actually is immediately consumed in a second reaction here, where carbonic acid undergoes a decomposition reaction and breaks down into carbon dioxide, which we would see as a gas in the form of the bubbles here. And if you remove carbon dioxide from H2CO3, what you have left is actually water. And in subsequent videos, we'll talk about how acids are synthesized by adding a non-metal oxide, that being a non-metal element paired with oxygen, into water in order to give us an acid. This is simply the reverse of that reaction here. So what we see is that after the initial double displacement reaction, we have a second decomposition reaction that occurs immediately after, and that is the source of the carbon dioxide that produces the bubbles in this characteristic reaction. Now, technically, most chemistry teachers would write this as a single reaction here rather than as two separate reactions. So what would that look like? Well, you can see that carbonic acid doesn't actually appear in the reactants here, because even though it is produced in this first step, in the double displacement reaction, the carbonic acid is consumed immediately after in the second reaction, meaning that because it is broken down into water and carbon dioxide, we would not expect to see this in the final chemical reaction, because effectively it does not exist anymore. So what we see, if we add the overall reactions together, we can take both of our reactants and they would appear right here, and because carbonic acid is consumed in the decomposition reaction, we don't see it anywhere. And if we simply take the products that exist of the first reaction, so in this case it would be sodium acetate, NaCH3COO, and the products of our second reaction, and join them all together for an overall reaction like this. Now, this phenomenon where the product of a double displacement reaction immediately undergoes a decomposition reaction actually does not just occur whenever we produce this compound here, although carbonic acid is an acidic compound that is prone to both being able to break down and be produced depending on the availability of carbon dioxide and water, but we can see similar decomposition reactions occurring with this acid here, which is called sulfurous acid, and with a compound that isn't an acid at all. This is ammonium hydroxide, which is actually a base. So if we take a look at the reactions here that occur, every single one of them follow the same format where we have a double displacement reaction followed by a decomposition reaction. So here, if we do the double displacement, we take our cation sodium, which is going to substitute for the hydrogen there, so that we get our characteristic double displacement reaction, giving us potassium bromide as our salt compound here, and then what is left is our acid, which in this case is sulfurous acid that we see here. Now this compound is actually going to undergo a decomposition just like carbonic acid, but instead of CO2 that this reaction produces, it's actually going to be SO2, and what remains of the original acid is going to be water, just like we saw in carbonic acid decomposition in the first sample reaction. So from here, because this acid is a product in the first step, but then is immediately consumed as a reactant in the second step, it doesn't actually appear in the overall equation, and all we need to do is add all of our products together in order to get the final reaction. So KBr from our double displacement reaction, sulfur dioxide, and water from the decomposition reaction after. Finally, if we can see that ammonium hydroxide is one of the original products that is produced, we can see what happens to it. So in this case, we'll do our double displacement as normal. Na plus and NH4 plus, sodium and ammonium, are the cations that are going to switch places in our double displacement reaction, and we're going to end up with ammonium hydroxide as one of our salt compounds, and then the second compound is just plain old ordinary NaCl. But what we're interested in is what happens to ammonium hydroxide after this reaction occurs. Well, ammonium hydroxide can actually undergo its own decomposition reaction, because we can see that we can actually get a water molecule out of this if we remove the OH and one of the H's here, which leaves behind NH3, which is a gas called ammonia, which is actually a very deadly poison if breathed in enough by humans. But this is one of the common features that we see of every one of these compound reactions, is that these reactions always seem to produce a gas followed by water that is left over in the decomposition. So yet again, because ammonium hydroxide is immediately consumed after it is produced, it does not appear in the overall equation, but NaCl, the product that does remain, would, and then the two products that ammonium hydroxide breaks down into, that being water and ammonia gas, would appear in the final stages of this reaction. And there we have a relatively predictable trend. We have a double displacement reaction that results in some sort of compound that can break down into water and some sort of gas as a result, and that's why the products of the overall equation, the double displacement and the decomposition after, look a little bit strange, but if you know that they actually come from two separate reactions, it becomes much easier to predict. This concludes our series on double displacement reactions and the nuances therein. To test your knowledge of, firstly, identifying precipitate formation, and secondly, identifying whether this compound double displacement decomposition reaction occurs, you can try the practice problems following this, firstly, writing out what the actual chemical formulas of the reactants are, identifying what the products would be if a precipitate occurs, and therefore if the reaction occurs, and finally, if any subsequent decomposition reaction occurs because of a compound that can break down into water and a gas in a second step.